Ya.
Bueno, pues el siguiente conferenciante es Boschheidgen, de la Universidad Autónoma de Madrid. Bueno, va a hablar en inglés porque se siente más cómodo, pero si os sentís más cómodos haciendo las preguntas en castellano, pues lo podéis hacer tranquilamente. Su Eigenvalue measure associated to this.
Okay, so thank you very much for letting me speak it. So my talk kind of fits in line with the previous two talks. I will also speak about groups, and I will also use a lot of analysis. And let me just tell you what I'm basically doing, what I'm interested in. And I start with the residual finite group, and the matrix over the group ring. The group ring is just all finite linear combinations with coefficients of C in the complex numbers, and of elements in G. And I choose the residual chain, like I choose a chain of normal subgroups with trivial intersection, all these normal subgroups of finite index. And then I can consider the groups GI as the quotient groups. And the matrix A I choose that acts, or actually every group G acts on the quotient groups. And so I get an action of the group of the matrix A on the group ring, on the nth power of the group ring. But now the group ring of the finite group, the linear combinations, it's just a finite dimensional vector space. So from this action of my matrix A on this group ring, I actually get it's a linear action of finite dimensional vector space. So what I get is a matrix AI. And now what I'm interested in is, okay, what can I say about the eigenvalues of these matrices AI? Especially what I'm interested in is the eigenvalue distribution. Like it might be these are some matrices that the eigenvalues of these matrices are just somewhere on some space, but there's no structure. But I'm interested in, is there structure, and does this structure depend on the chain I choose? And to convince you that what I'm actually doing is interesting, let's just consider an example. And the easiest group we have is just that, the integers, it's a cyclic group and one generator. And let's consider this matrix. Not difficult, we have integer coefficients. And as a residual chain, I choose an I is the ith power of 5. And then I get these groups. And let me just give some chalk. Just to make sure how these matrices AI would look, I just would send X to the matrix 0, 1, 0, 1, 0, 1, 0, 1, 1. So that would be, in the case I is 1, that would be the image of the matrix of this X. And then X squared, I would take this matrix squared, and so on. And if I is 2, I would have the same until 25, and I have 3 until 125. And so I build these matrices, and I can look what the eigenvalues of these matrices are. And I see at least there's something. Actually, there's a lot. I mean, we have this blue line, so it's kind of, this blue line is, okay, like the red dots are just the eigenvalues, and I also have this blue line there, so we see that there's all the eigenvalues lie on some line, on some one-dimensional thing. And in fact, it's really like this blue line kind of describes some limit thing. We will come back to this later. The problem is now, we see that there's some convergence, but how can we measure this? I mean, eigenvalues of matrices are just like points. So the set of eigenvalues it's maybe a multi-set because we have multiplicities, and we have no idea like how can we measure the convergence of multi-sets. And what helps is this analysis in this case, because we can define a measure. For any matrix, matrix B of the complex numbers, we just pick the eigenvalues, and n-dimensional matrix, we have n eigenvalues, and we just put on any eigenvalues, we put a direct measure, and then we take the sum. So actually, we just count for any subset. This measure would just count how many eigenvalues of my matrix are in this subset. And now we have these measures, we could associate these measures to the matrices AI, but this will make so much sense yet, because we have to do something more, because the first matrix in our previous example was of dimension 5, actually of dimension 10, the second of dimension 50, the last one of dimension 250. So we somehow need to scale, because these measures can converge if the total math is growing. So what we do is we just scale them by the cardinality of our quotient groups. And then we can talk about different conversions of measures. And there are several notions. There's weak convergence, strong convergence, and conversion total variance. What we'll focus on is weak convergence of measures. And weak convergence just says that for every continuous function, the integral converges. Actually, we want to have here the bounded function and also compactly supported. But this compactly supported, we don't really need to care about this, because we have this. All these matrices AI come from some limit, come from our original matrix I, and that gives us a bound on the operator norm of all the matrices AI. And so we already know that all these eigenvalues are in some unit, some disk around the origin. But now, why should there be convergence? I mean, we saw it that they somehow all line up. So there is some convergence. I want to kind of explain where that comes from. And imagine the matrix A is self-adjoint. Self-adjoint, then also all the matrices AI are self-adjoint. And self-adjoint matrices have the good property that all the eigenvalues are on the real line. And now if I take some function on the real line, we remember also the measures are compactly supported, so actually if I have a function on some interval, then I can approximate this function by polynomials. This is the Weierstrass approximation theorem. So actually all I have to do is I have to see what happens with these measures in polynomials, and because they're linear, I just have to look at functions of the form x to the power of n. Okay, now let's go to the pick some matrix with self-adjoint matrix. So I have eigenvalues on the real line, and I want to calculate this integral x to the power of n. Okay, then I put I just sum at the eigenvalues. Eigenvalues to the power of n. But the sum of the eigenvalues to the power of n is just nothing else but the trace of the matrix to the power of n. So basically, what I have to make sense of is this expression here. I need some limit of the trace. And how can we define this? And let's think about where does the trace of these matrices come from? I mean, let's say we have our matrix A is one-dimensional, so it's actually just an element from the group ring. And then this action of G on the quotient groups, that's represented by this action, by this matrix, this action permutes the elements of the quotient group. And if I have something on the diagonal, which would give me a trace, then it just means that I fix the whole group, that I act trivially, that I fix some point. I mean, the elements on the diagonal are kind of the fixed points. Because I have a group action, if I fix one point, I fix all of them. Like, okay, not because I have a group action, but because I have a permutation group action, I act on the cosets. So basically, I only have an element that gives me a trace if my group element comes from this normal subgroup, is in the kernel. So it acts trivially on my quotient group. But now it chooses this a normal irresolute chain. I have the intersection of all my ni was trivial. And in my matrix A, there are only finitely many elements. So at some point, I'm going down, 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 and there's no element left in the kernel, no element left of the matrix, no element of the matrix appears in one of the ni's. And so nothing appears as a trace anymore. And that's why we can make sense to define the trace like this. So if we have a group G, and here we pick an element of the group ring, and then we say the trace is just the element, the coefficient of the identity. And if you think about this in the limit, this is exactly the same as a normalized trace of the AI. And actually not only for the AI, but also for all polynomials in the matrices AI and AI star. And then we see, like, from this previous equation we had, we want the limit here, we get the limit here, and this is just the same trace. And now we basically have a limit measure. because we were talking about the limit measure on the real line, I convinced you because by the Weierstrass approximation theory, we just need to focus on what happens for polynomials for powers of x. And I know what happens for powers of x. So this limit measure is just defined by our original matrix A. By the way, I was just talking now about self-adjoint elements. This same thing works still for normal elements. There you need more moments. You need to look at you need to trace of A n A star n. So this is the adjoint matrix. Because in the self-adjoint case, this is just the same. So you only end up with powers of A. In the normal case, you need some more, but it still works. Just becomes a little bit more complicated. But now we can also, this limit measure, we found out that it is defined by the trace. And analysis actually gives us what it is. Because let's go back to our matrix A. And this matrix A is also an operator on a Hilbert space. Let's first construct this Hilbert space. We have the group ring. This is just the group algebra. The finite linear combinations of group elements with coefficients in the complex numbers. And we can define in this way an inner product on this. Now we have a vector space, we have an inner product, and then this inner product defines a norm just by the inner product of x star. This gives me a norm. And so we get a Hilbert space. Because we can complete the vector space with respect to this norm and get a Hilbert space. Hilbert space is a complete vector space with the inner product. And so an element of the group ring now acts as a bounded operator on this Hilbert space. Just for that you know that L2 of G, this is also the sum of A, G, G, and we have A, G squared smaller than infinity. So if we have this L2G is just all square sum of the sums over G. The CG, the group algebra, is all finite sums. Of course, all finite sums are square summable, because of course it's only finite. And in the completion, I get all square summable sums. And now I know that this group algebra acts as a bounded operator on here, just by right multiplication. Also by left multiplication. So we actually get two representations, but you can choose first. And so I have an operator, and if my matrix A is normal, so all this can be extended to matrices and to L2G to the power of n. But that's why we're talking about matrices. That doesn't cause any problem. And for self-adjoint normal elements, we have a spectral theory. And we have a recent representation theory, and that gives us a spectral measure. First, a spectral measure, it's a projection valued measure, but if we concatenate this with a trace, we actually get a probability measure. And this is our limit measure. And actually, for the self-adjoint, for the normal case, the story is told. We have everything. Just the convergence in trace gives us the convergence of the measures. But for arbitrary elements, I mean, this eigenvalue measure, you can define for any matrix. And also for arbitrary elements in the Tercera phenomenon algebra, you don't know what that is, but let's just say for arbitrary matrices over the group ring, they are also operators, and you can still define a measure. And you could ask now, okay, maybe if I look at any matrix that is not necessarily normal or self-adjoint, and I get this series and I have convergence in trace, then I also get convergence in measures. this conjecture. But this is actually wrong. So in the normal case, everything is fine. In the non-normal case, we have a problem. Because we can look at these Jordan block matrices. So I just have zeros on the diagonal, ones on the upper diagonal. And if I look at the definition of the eigenvalue measure I gave you before, I just put in put a direct measure at every eigenvalue. The only eigenvalue is 0. I just get the point measure at 0. But in traces, you can't in traces, this element converges to this value. So if I take any polynomial and this series of matrices where I make this bigger, and this series of matrices where I delete the one here, the one I gave you before, in traces I don't see a difference. And the limit will always be the same. And so I can't decide these. But I mean this element x, it's a unitary element, it's normal, and the spectral measure is just unitary the measure on the unit circle. And the problem is that the AI are not normal. So I already told you, like, if I change this matrix slightly, so this was a common example, if I change this matrix slightly, the trace won't change, but the measure can change completely. For example, if I just put an epsilon here, and so just imagine the matrix is way bigger, like, I don't know, dimension 1000, and I put a fixed epsilon, or I could even, let's say, 1 divided by n, where n is a dimension, then in traces nothing changes, but the eigenvalues of this converge to the unit circle again. So a very small change in the matrix gives me a huge change in the spectrum. In normal elements, this does not happen. In normal elements, for normal matrices, this does not happen. If I have a normal matrix, and I add a small perturbation, like something in operator norm small, then also the maximum distance between the eigenvalues of the old one and the eigenvalues of the new one, they are still small. So in normal matrices, this is kind of stable. But if I go to a non-normal matrix, I have a huge problem. And so when I have this homomorphism, where all the AI are normal, then I'm good, I'm fine. Actually, you can show that if you have some limit matrix, and you have a series of matrices that converges in trace, you can always find a small perturbation. Like you can always find this other series of matrices that vanishes in the limit, that goes to 0, so that you add it to our original series, then they still converge in trace, but then the ground measure, the eigenvalue measures also converge. So you can always fix it by a small random so you can always fix it by summing the small matrices to it. But let's go back to our example. And the matrices are not normal. The matrix A is not normal, and so the matrices AI are also not normal. And we still see that there is convergence. And at least in this case, we can say something. So for any groups, when the matrix A is normal, everything is good. But when A is not normal and when G is abelian, there's something we can do. Actually, when G is abelian, then we have reconvergence. So where does that? We actually look at the regular representation of our quotient groups. So we take the quotient group as a vector space. So we take the vector space with basis the quotient groups GI, and these are also abelian groups. And any regular representation of a group that decomposes as a direct sum in the irreducible representations. And irreducible representations of abelian groups are one-dimensional. So if I look at these matrices where ascended, here 1 again, I can change the basis. Let's put it all there. I can change the basis, and then I send it to this matrix 1, and then E2 pi I. Let's say in the case of 5, 1 over 5, and so on. E2 pi I 4 over 5. And I send it to a diagonal matrix. And now I have like a diagonal block matrix. So my matrices I would be something like this. I have something here, 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 and here. And now I'm interested in the eigenvalues of those. And I can calculate them quite easily because these matrices all commute. And so what I get actually as a determinant of the matrices AI is just the product of the determinant of our matrix X is 2p x to the power of 5 is 1, that still exists, and then lambda minus a. So I have this matrix A in the beginning that had an element x, something there, and actually what I do is just plug in for x all the numbers on the unit circle that come from my from my representation. I plug in all the irreducible representations. So I just have to plug in all these numbers here. And then I end up with something way smaller. I end up with something n-dimensional, a product of something n-dimensional, and so I can calculate what actually is the limit measure. So the trick here why this works is that I actually have a bound on these irreducible representations. So I get something just as I get the limit as something as a sum or direct sum or direct integral of something very small, something one-dimensional, or not one-dimensional, but from the dimension of our group, from our original matrix. Now let me tell you where all this actually comes from, and why we're interested in this. For any matrix, the dimension of the kernel of a matrix is just the eigenvalue measure in 0. I mean, the kernel is just how often the eigenvalue 0 appears as an eigenvalue. Of course, and we want to generalize this, and we can also define the dimension of some subspace as a trace of the projection. And this is, like, the first part is kind of difficult to generalize, but this one we can generalize, because for this we only need projections and traces, and then we can define dimensions. And this, both we have in the phenomenon algebra setting. You talked about this also. And the phenomenon algebra of a group is, I told you that the group ring acts as bounded operators on this group Hilbert space. If I take the weak closure, like the definition of phenomenon algebra is that is weakly closed. So if I take the weak closure of this group algebra in the bounded operators of the group Hilbert space, I end up with the group phenomenon algebra. You know, this phenomenon algebra, I have a tracial state. I have a trace. This is defined like I act on the one is a one in the group. I act on this on the one with the A, and then just take the inner product. And this we can, okay, this is first only defined in the group ring, but this we can define this also for the group algebra. And with this we can define a dimension as this. We just take, if we have a subspace, we take the projection onto the subspace, and then we take the trace of this projection, and we get a dimension. Okay, as I said, all this can be generalized to matrices and to matrices over the group Hilbert, group phenomenon algebra, and to the direct sum of the group Hilbert space. And now we have dimension, and we can say the dimension of a kernel of a matrix. We can say that the rank of a matrix is just n minus the dimension of the kernel of the matrix. And now what we can ask, all this, what I said before about the conversion in the 0 of a measure, or what if the rank are equal, all this becomes the measure theoretic equations if we have convergence in 0 of these measures. So we know that these measures converge weakly. So if we take integrals over all functions, then we have convergence of the integrals. But what we're now interested in is if these measures converge in 0. This is, okay, similar but different. And the good thing is this weak convergence of measures already gives us something, because it gives us one direction. The weak convergence, this is the theorem of portmanteau, and this here, and this is what we're given. This just came from the trace. We had this trace convergence. Because this is equivalent to this, to the second part, for all closed sets, we get one inequality already, because 0 is a closed set. So we already get 1/2. The second part is more difficult. For this, we somehow need, well, what it turns out that we need to control the spectrum near 0 of a matrix. Because when we control the spectrum, we have like a function that controls, that bounds the spectrum near 0 of all our matrices AI. So this UI was the spectrum measure of our finite dimensional matrices. And we have this, the bound here, then we can easily deduce the other equation. And this was originally done by Wolfgang. And I'm kind of out of time. But we have this one. We have this theorem of Wolfgang that for integer matrices, we have a uniform bound on the spectrum near 0. And I'll just tell you what the key ingredient is. It's basically here. So we fix one I. We look only at one matrix, and we say that the matrix is integer coefficient. So we say that the original matrix I was over the integer that we bring. And so all the matrices AI also have integer coefficients. And now here we just kill all the 0 as a multiplicity in the characteristic polynomial, and then the characteristic polynomial satisfies this equation. The lambda I to lambda s, these are all the lambda 1 to lambda s that are the non-zero eigenvalues. And then I can kill kind of the 0 as the eigenvalue, and then I still have here an integer polynomial, because I just divided by the biggest power of x possible. And the point is, I end up with this equation because I can plug in x equals 0, and I get something like this, because this integer polynomial at least has to be 1. All the lambda 1 to lambda s are greater 0, and the left side then is just the product of all the lambda 1 to lambda s, so its integer has at least to be 1. And then what I do, I find some bound here, and then I take the logarithm. The logarithm of lambda, and I get something null. 0 is smaller than something. And if I do sum of math, the easy math is log lambda is smaller 0. And so I can, this here, at the end goes, is great, if the absolute value is greater 0, it goes to infinity. And so I get some I get some uniform bound on the spectrum. So, but the key ingredient is that we have still integer coefficient. That's all we need. And yeah, that's all I wanted to say. Thanks for your attention.
Thank you very much. Just a more comment, just to thank you, because you clarified the previous question I put before. Now, again, I was thinking of the case of in a group, and now I see, for example, that the Von algebra is exactly the algebra group.
Yes.
So, thank you very much again.